Okay.
Okay, welcome to back to the second half. What I'm going to do now is, I guess, deep dive into the whole landscape of machine learning as it pertains to data analytics. Okay. Now, remember I told you that there are like 4 blocks of things that we can spend our times on. That's interactive visualization, statistical method, and machine learning. And you can see why I put this data mining as a third bit. It kind of like doesn't really fit very much. Okay, you can stick that inside. It's not quite statistical methods, not quite machine learning, and I cover it again because it's useful and it's not a particularly interesting subject, but I stick it there. So basically this, and this. Okay. So with interactive visualization, guys, it's kind of like it's one of those things where you get insight in a Zen-like thing. You know what a Zen philosophy is? The idea is you kind of like ponder some kind of riddles, right? But once you make this kind of mental leap, you get the picture, you get the insight. So it's not algorithmic in the sense that you can't trace into different steps like a mathematical proof, but you sort of like arrive at insight. Well, visualization, interactive visualization is supposed to do something like that. It doesn't feed into statistical method, machine learning tools or anything necessarily, but somehow by plotting X versus Y or plotting effect of X versus effect of Y over time, you get immediate insight and you know exactly what you need to do. Okay, so you can see why even though there's a lot of hard geology or physics or geothermal physics that goes into the science of climate change, the most important insight in terms of climate change comes from interactive plots. Like say, what's the average a temperature as a color, right? Red for hot and blue for cold. And you can do sort of like interactive from before 1800 to 1900 to 2000 to today, that sort of thing, okay? Or occurrence of wildfire. So you see that interactive visualization in many cases is all you need to get the right insight and to make the right decision. Like right now, something is the world is heating up, guys. You can't really be planning an economy based on fossil fuel anymore because the world is just heating up, and that you don't need to fit any kind of statistical. Sometimes you just visualize, and that's it. Okay, so the world of interactive visualization is a bit like that. Sometimes when you put the data in the right color, the right dimension, the right plot, cover over time, compare this versus that, you versus me, Thailand versus the world, Asia versus Africa, all kind of stuff. Once you did this, you get the insight. Okay, it is in a way, it is the analytics. Just the picture is the analytics, and it immediately informs. Now, that is sort of like the end user. Okay, there's an element of interactive visualization, the second part, which is informs the model building approach. That means that you are still going to do statistical method, you're still going to do machine learning, but which tools, which algorithm to choose, what kind of family, choosing the right P. Remember I tell you, choosing the wisely, choosing the distribution function wisely. How would you do that? The first clue to it is just to look at the histogram. Right? So that's visualization. You try different visualization, so interactive visualization. And finally, so that's why I have this thing I want, before I go to machine learning, I want to show you that interactive visualization has 3 things going for it. Number 1, the visualization is the analysis. You see the picture, you get the Zen-like realization what the problem is. Second thing is, you as a data scientist, use it yourself, so that it informs how you should build the model. It helps you build them. I do that. Before I build the model, I don't download the data and build the model. I download data, I do interactive visualization, get an idea of where things are and so forth. Then I do the machine learning. So it informs me. The user is the data scientist. Finally, if the data scientist build the analytics, make the statistical conclusion, makes the machine learning prediction, how do you present the result? Well, you can present as a table of numbers, but your client or your end user is not going to get the picture. So interactive visualization is the communication tool. So that's the third aspect. Okay. So again, the first one is, it is the analytics. The second thing is it helps build analytics. The third thing is, once you build the analytics, use the analytics, this is how you present the result. Okay. And that's very powerful. And I've been to, countless academic presentation where, the talk is very interesting, but the result of the experiment is a table of numbers. And you look at it and it's sort of, what's that number saying? Okay, maybe there's a little star that says statistical significant. But if I see actually interactive plot between this dimension, that dimension, it's much better. And I try to do that with my academic papers as well. Okay. In fact, a lot of time I do interactive plots in Mathematica, and I just take the screenshot of that and put in the academic paper. Okay. Okay, so let's go to machine learning. First of all, oops, go here, right? Okay. Now, this is something I want you to pay very close attention. It's a little bit abstract. Okay. Machine learning. Machine plus learning. Obvious enough. Machine. Okay, let me expand this and then you can see what. Yeah. What's a machine? What's a machine? Yeah. Well, first of all, it's a construction. It's not something that's for us anyway. There's a natural machine like photosynthesis machine. Okay, we don't create that. That's not our job. Okay, that's done for us. So it's something that, in this case, machine is something that we create. Okay, when I say machine learning, okay, let's say we go back 400 years. We had the notion of machine. Okay, we didn't have the notion of machine learning. What did that notion of machine involve? Well, machine is sort of like a tool that does something for us. It performs some kind of task. Okay, so it performs some kind of task. So, an irrigation machine, what does the task it do? It, brings in water into the field, and when there's too much water, it directs it elsewhere. So machine does thing for you. Okay, does thing, performs some kind of task. With machine learning, it's essential that that machine perform two tasks. Okay. Now, before the age of machine learning, you create a machine to perform a task. Okay. So the machine performs some task for you. That's it. That's its purpose in life. With the age of machine learning, you have a new kind of machine that cannot perform the task yet. The first task it has to do is for itself, and that task is called learning. Okay? Now, let me give you an analogy. I have a tractor that plows. Once the thing is built, you can use it to plow the field. So there's only one task to do. right? Now, instead of having a machine that plows, you have a child that plows the field. Can that child plow the field right away? No. So the first task that child has to do is to learn the task. So it's always a two-step process. So with machine learning, the essence is that that machine always has to go back and forth between two jobs. And this is relevant from 50 years ago all the way to ChatGPT. Okay? And it tells you the strategy of how you can adopt the technology. Let me give you an example. When the language model is small, I can download it, give it some data, ask it to learn. Once it learns, it can do things for me, like chatbot. Okay. Nowadays, it turns out that the learning task is so extraordinarily expensive that nobody can do learning tasks except 5 companies in the world. Let's say, okay? There are, for large language model, okay? There are only 5 labs in the world that can do learning tasks. Okay? Everybody else go to performing tasks because you can't retrain that. Now, there's a nuance to it. So there's a little bit of retraining. There's a little bit of a specialization, alignment, all kind of stuff. But essentially, the big chunk of the large language model, nobody, and I mean nobody, can perform. Okay? Only OpenAI, Google, Meta, or Facebook, and a few other labs can do it. Yeah. But anyway, so that's the whole point. So it's a machine that does 2 jobs. And how it does the second job depends on how well it does the first job. Okay. So in that case, that machine, that's why it's more like a human being, in the sense that a human being is completely useless until it learns. Well, same with you, right? Right? Let's say you go to an engineering school, so you become an engineer. You're useful as an engineer, but you're useless before you enter engineering school. Right? Nobody's born an engineer. Okay, so you have 2 jobs. One job is to educate yourself, go to university, get the degree, becomes an engineer. Then you can become useful. It's always a 2-step. And how well you do the second step depends on how well you did the first step. Okay, same thing. Now, let's talk about, so the machine does two tasks. That task is called, the first task is learning. There are 2 things that you have to think about in terms of learning. There's learning basis. Where do you learn things from? An algorithm. Algorithm is how you learn. Okay. Think of basis as your data environment. Okay. Let's say how you learn is you read a book. How you learn is you read a book. But the basis of your learning, you have one guy who has 1 book. The other guy, he has access to a library. Who's going to be smarter? Right? Same algorithm. That algorithm is called read the book. Okay? But the asset with which that first guy has is just 1 book. The second guy has a whole library. Okay? That's called the basis of learning. Now, in most applications, the basis of learning comes from what's called empirical evidence. This is where the data. So the bulk of data, machine learning from data, this is here. You get empirical data. You get bunch of X, you get bunch of X and Y, you get bunch of whatever. This is your empirical data. So it's based on or from historical data. When I say historical data, I don't mean, because it's history, it just means it happened already. Okay? Now, there's a second kind of basis of learning. It's called simulation environment. this is going to be more and more relevant. Strictly speaking, let's say I go back 3 years ago, I can ignore, I don't even have to mention this. Okay, you basically learn from empirical data. But now there's like simulated things you can learn from. And this gets us all the way to, generative AI and whatnot. Okay, but still, I'm not going to pay too much. But instead of having a real thing that happened, you can have something that generates something and learn from it. Think of it this way. If you learn about the traffic in Bangkok by walking, okay, that's learning from empirical data. But if I have SimCity, okay, and I name it Bangkok, SimCity, and then you walk through that SimCity, is that real data? No. But is it generated, and does it allow you to learn certain things like, turn left when the street is whatever? Yeah, it does allow you to learn something. But the basis came from generated data. Now, this is going to become a lot more relevant in your generation. Okay? When I say simulated environment, you can be general and say includes everything that is not real. So even fake news, if you have a large language model that reads from fake news, that would be like a simulated environment as well, right? I can have a fake news that say, Australia is a landlocked country. Okay? Imagine that, right? Imagine in this simulated world, there's like an internet troll that keeps saying that Australia is a landlocked country, it doesn't have a beach. Okay? And this occurs so much in all the tweets and all the Wikipedia, it just trolls the internet. Australia is a landlocked country. Now you feed that into a large language model. What's going to happen? Tell me about Australia. ChatGPT is going to say, oh, Australia is a landlocked country. You see what I mean? Right? So the basis of learning can be real from empirical or can be literally simulated or made up. Now, there's another thing called tacit evaluation, and this is a little bit hard to, it's a little bit like simulated environment, except it's sort of like a reward punishment thing. I'm just gonna not talk too much about it. But here it is. Now let's go to algorithm. Okay. What makes a good algorithm? Well, a good algorithm is good accuracy. Okay. But that's not good enough. Here's a trick. If I'm drawing, if I'm drawing a portrait of you, okay, and it looks realistic, that's called perfect accuracy. Perfect accuracy, right? But if an alien come and ask me to draw a human being, and I can only draw one face, the alien is going to have a wrong idea of what human being looks like. Because just one face. So the alien is not going to understand the concept of human eyes because it's only got one eye to look at. Okay, let's say you're wearing glasses. So I'm drawing you, right? Aliens are going to assume that human beings always wear glasses. Perfect accuracy. High resolution image of you, perfect accuracy. But absolutely zero generalizability because it overfits. Now, it sounds obvious, right? It sounds obvious, but that is where the art of data science is. It's the playing between accuracy and overfitting, or ability to generalization. So accuracy and generalization, those are sort of like two things that it's always in the back of your mind. Okay. Your job is not to draw a portrait. If your job is to draw a portrait, that means you have 5,000x, you fit perfectly 5,000x. But when you get the 5,001x, it's nonsense, right? So the idea is that you're not trying to fit the perfect 5,000 cases that you've seen. You fit as much as is generalizable. Now, I'm saying this right now, it may not mean anything to you, but believe you me, this is what separates professional or really good data scientists from a lousy one. Okay? Everybody can learn to code. Okay? But until you know how to balance accuracy and generalizability, you will never make a good data scientist. Okay? So you always lose sleep over generalizability. Anyway, so that's a concept of, well, a machine has to do two tasks, one for itself to learn how to do things, then it can do useful things. And that useful thing is predicting y given x, right? And how well does it do it? Well, it does it really well with respect to the data it has seen, but it has to be able to generalize to the case that it hasn't seen. Because after all, again, you're never interested in the sample. The data is a recording of the sample whose general population you want to analyze or get insight. So if it only gives a perfect fit for the sample, but doesn't generalize to the data, that's not good, right? Now, oops. Okay, so that is okay, machine plus learning. Now let's go to learning plus machine, for lack of a better word. Okay, so let's not focus on the machine. Let's focus on learning. Start with learning, okay? Again, if you start with the machine, it has to do two jobs, right? And how it does with respect to one job depends, on the other job. So if it does on the learning from the data, it does too good of a job, it overfits, okay? That sort of thing. Now, let's flip the other way definition around. Instead of machine learning, start with machine, let's start with learning first. Now, learning is the word that adopts from human learning. So let's think about how human being learns. Okay. Now, this I have to talk, even though this is not a class about machine learning, you have to learn this. There are actually, oops, how to expand it. There. How a human child learns. So exactly the same analog. Okay. Now, you can close your eyes if you like. When you were a baby, you didn't even understand language, right? You didn't understand language, right? But every time you get this smell, you get fed. The smell is your mom. And you get warm milk, okay? Nobody taught you anything. Nobody taught you anything, okay? Well, something else. Evening times, bath time, you hear running water. And soon enough, you get cold, it's not comfortable. It's not a nice feeling because you're like thrown in the bath. This automatic association. Nobody taught you anything, but you make this association, okay? So in a way, because you're not taught, okay, it's called unsupervised learning. Why is it called unsupervised learning? Because the parents have no control over what the child learns. Okay? Bath time, parents don't want to associate bath time with suffering. Okay? They don't. But every time there's a water running, the child gets thrown into cold water and he doesn't like it. He's not comfortable, he cries. Okay? The parents have no control over what he learns. Okay? Same thing. The smell of mother is associated with milk. Fine. And the sound of really loud human male, is associated with maybe smell of smoke or something because the father smokes too much. Does the father want the child to associate him with the smell of smoke? No. But because every time he shows up, he smells like cigarettes, the child makes that association. He cannot control. So the only thing that happens is that there's some kind of implicit association algorithm in the child's mind. Associate smell, taste, touch, temperature, hearing, sound, sight. All these things are built in, right? A child has all this capability. The fact that the sound of a human male and the smell of cigarette comes together, that becomes connected in the minds of the child. That's automatic. So this is what's called unsupervised learning. Okay, it's the first mode of learning. Okay, it's basically association. Now, what happened when you start to learn the language? Now, the parents bring you an apple and tells you this is an apple. Brings you a banana, tell you this is a banana. Next day, the mom brings in a fruit and show it to a child. What is this? So, first of all, a child is shown a pairing between this thing and apple, this thing and banana. That is a sample. Okay? The learning hasn't happened yet. Okay? The learning is association is happening, right? Association happening. But sometimes you can have long apple and maybe round banana. I don't know. Just say it's not perfect. Okay? And you bring this thing, it's supposed to be an apple, and the child say banana. What do? You tell your child, no, little Johnny, this is not a banana, this is an apple, right? So what happened is that the association that the child begins to form is not crystallized, and it may be wrong. The job of the algorithm is to give immediate feedback. The key word is immediate. The child knows right away, when I see this thing and I call banana, wrong, apple. Okay? And this loop goes over 1,000 apple. Okay? So you would think that when a child looks at an apple and says it's an apple or banana, that is performing classification task. Not yet. Because that classification task is still within the learning period. And that classification can be wrong. Right? So the job of the mother is to keep giving association between this and apple, this and banana, and more importantly, correcting or affirming. If it shows a banana and the child say banana, you say, good, little Johnny, good. If it's banana and says it's apple, you say, no, bad Johnny, that's apple, that's not banana. So it's immediate feedback. That is called supervised learning. Again, I haven't talked about a machine. I'm talking about a human being right now, right? Because I'm starting from learning. Then there's something else. What if you're not given immediate feedback, but you get to receive feedback over a span of period? Let me give you an example. Okay. So when a child is born without the benefit of language, that's unsupervised learning. You start learning language. This is apple, this is orange. Now the child goes to kindergarten. Okay. Now, let's say the child is talks all the toys, doesn't share the toys. Okay. Nobody tells him anything. Okay. But he doesn't share a toy. Okay. What happened? Over time, is this child going to be liked? Is somebody going to say, oh, come play with me? No, he's going to be excluded. It's kind of a sad feeling. So it's a feedback, but it's not immediate. Okay. If you have this helicopter parent that say, oh, Johnny, you should share, that's supervised learning. Okay. But if the child just kind of experiment with his behavior, if he shares, people like him. Okay. If you show up on time, people like you. You dress professionally, people give you important project. This thing, nobody, if you dress, if you don't care, just come in sandal to a job interview. They're not going to tell you, don't do that, right? But if you wear sandals to interview 5 times in a row and you never get a call back, right? And this kind of internal loop works in your mind. Hey, the other time I kind of wear proper shoes to an interview and I address by sir and I'm polite. I get called back right away, even though, I didn't answer the question right. So this kind of association over a long evaluation loop. Okay. There's this kind of evaluation in the back, evaluation engine. So that's kind of feedback that happens over a long period of time. It's not immediate. But soon enough, you learn that when you act respectfully, people act to you with decency. You share your toys, kids like you. Okay, that sort of thing. This is called reinforcement learning. Good behavior or behavior that are considered positive gets reinforced. Behavior like not sharing toys or punching the next kid or something like that. Okay, so in the next, okay, let's say this is a final exam. Okay, little Johnny punch Bobby, and the teacher comes in and say, "No, Johnny, that's bad." A, is it unsupervised learning? B, supervised learning? Or C, reinforcement learning? What's the answer? Final exam. Supervised learning. Okay. Johnny keep punching everybody, and by the end of the semester, by the end of the term, nobody talks to him, nobody shares candy, and he feels really sad. A, supervised learning. B, unsupervised learning. C, reinforcement learning. All right. Okay. So these are the basic learning paradigm. Has nothing to do with machine yet, right? But say on a final exam, I can ask you this. So the paradigm, the keyword is paradigm. Now, this for the longest time are the 3 main machine learning paradigm. There is a 4th machine learning paradigm that I will call embedding learning. That is extremely important within the context of modern AI. This is how generative AI works. This is how large language model works. You can say that, yeah, it is a combination of unsupervised and supervised learning, but sometimes modern AI researcher would say there's a 4th paradigm. Okay, but never mind. Yeah, the reason I say never mind is because even in this class, I'm going to throw away one thing. I'm going to throw away reinforcement learning, because reinforcement learning is not as applicable to data analytics. It's applicable to, anybody want to guess? Robotics, right? Because the robot can experiment what happened when I send a sensor and there's a signal and I hit over here and I hit something. That's bad. And I just, so instead of a child punching his classmate and then nobody likes him, he feels bad, it becomes a robot, like a Roomba, okay? And it runs through things, it has a sensor, and every time it hits something hard, it gets a negative point, and this accumulates over time. Okay, something like that. Like, if the Roomba keeps going like this, it's going to run out of battery without getting anywhere. But if it does this, it can save the battery, it can accomplish the task and so forth, and then get the reward at the end or something. Okay, that becomes reinforcement learning. That is very important. In fact, if you're going to study robotics, let's say you go for applied digital intelligence and you want to go big into robotics, your life depends on reinforcement learning. Okay, but in this class, in data analytics, the machine learning paradigm that you are going to rely on are supervised learning and unsupervised learning. Okay, so if that were the paradigm, Now, it becomes a matter of and this is, you don't have to pay attention to this. This is actually, well, you may if you want. Okay. What kind of machine are capable of learning? Okay. There are actually two kinds of machines capable of learning, but this one is not part of the curriculum. It's called quantum computing. This one is what you do today. It's called von Neumann. All the computers in the world that you use is called von Neumann computer. Okay. Just no mind. By the way, have you ever seen the movie Oppenheimer? Any of you watch? Okay. Well, von Neumann was a very important person in there as well, but it's one of those things where people criticize this movie that he didn't get a role. Okay, so you didn't see von Neumann. You actually saw people like Richard Feynman, you know, the guy who sit behind the truck during the explosion and say, you know, this is going to shoot. And the guy who plays a bongo, I don't know if you saw that, that's Richard Feynman. So these are little sort of like, little, what do you call it? When you stick in little nuggets in a movie, what do you call it? Yeah. Easter eggs. There's a lot of Easter eggs about Richard Feynman. There's no Easter egg about von Neumann. But anyway, von Neumann is one of the most important person. Anyway, so I'm going to skip that. So let's go deep into statistical method. Now, and again, there are I'm going to do this. I'm going to say this. There are three families of machine learning. Three families of machine learning. Okay. One family of machine learning is kind of probabilistic in nature. It's a little bit like data mining. Okay. It's learning some kind of probabilistic association. Okay. We'll call this kind of like heuristic or, you know, machine learning methods or something in general. Then the second family is a machine learning that deliberately mimics the human brain. Okay. And this is the whole world of artificial neural network. Okay. Neural comes from the word neuron. Network, because the output of one neuron is connected with other neurons and all the neurons are connected in a network. Your brain, for example, is a network of neurons. Your brain is a biological neural network. But instead of having a biological neural network, I have artificial neural network. Everything from, you know, image recognition in your phone to ChatGPT is in here. Okay, it's in here. Okay. Finally, there is this thing called evolutionary learning. I'm not going to cover this at all. It's a little bit too far. Okay, but that's way beyond. So these are the two set of machine learning, two family. For example, if I'm going to teach you, let's say next week, not if, next week, you're going to learn about decision tree. Decision tree is a way of doing some kind of classification. And it's based on conditional probability. At no point is that model based on how a neuron works. So where would it go? It would go here. Right? So you can say like neural based or ANN based and everything else. Okay? Everything else except this one. I'm just going to ignore this one. So in terms of probability, obviously, there's always supervised. Again, I'm going to dig deep into the details of machine learning for data analytics. So what am I going to talk about? Supervised learning and unsupervised learning. Okay, this is the I'll talk about it when in due time. I just have to tag it. Anyway, so let's go to unsupervised learning. Okay. There are roughly, so again, I'm giving you sort of like a game plan for the individual thing. So what happened when we come back next week, we're going to go into individual techniques. Okay. But let's say, I'm going to say that there are 3 problems that unsupervised learning machine does. Okay. This is different from a human being. Okay. A human being associate the smell of mom with milk, smell of sound of dad with smell of cigarettes or something like that. Okay. Let's say, that's, of course, my dad doesn't smoke, but I'm just making that example up just to have something that stick in your mind. Anyway, so in technical or machine learning, not baby learning, in real machine learning, unsupervised have 3 kinds of problems. Okay, they are closely linked. And sometimes you see one algorithm used for multiple tasks. But let's say, I'm going to say these are 3 jobs. Remember when we talk about statistical method, that's sort of like, what's the job? The job is to say, well, what's the probability of the value of X? What else? What other job can it do? Well, give me what the Y should be if you knew X. If I know what the height of the next person is, can I guess the weight? Or if I know the grade, I know the age, I know the location, can I predict the salary or something like that? Okay, so that's the job. Well, unsupervised learning does 3 jobs. That's 3 jobs. I have a whole bunch of entities. Okay, is there a natural grouping? Okay, is there a natural grouping? For example, and I find this really funny. They always say that, you know what a bell curve is, right? When they grade people on a bell curve, people are graded on a bell curve. Well, that works when you have like 100 students or something like that. And when the topic is kind of like generic. But for difficult technical problems, you know what happened? You know what I find? I find that there are always 3 clusters. There's like top student, there's middle of the road, and there's students who get lost. So if you look at their final grades, you don't get this kind of distribution of curve. You get this kind of 3 bumps. Really, I find that in real life. Okay, in real life, I don't when I grade you guys. Okay, I've been teaching, even though I've been academic for 2 years. I've been teaching since I was a student. So instead of seeing this nice distribution of grade, from 60 to 90, what happened is I'll see a few guys who's like probably should fail. Okay, and there's like no grades in between here. So from 60 to 79, nobody gets that grade. And then there's a big lump of population between 79 and 89, let's say. Okay, and then there's a gap, and then there's like top kids, like 95 to 100 or something. Okay, think about it. If I see that, what would be my conclusion? I would conclude then that there are actually 3 clusters. Natural grouping. There's a natural break between the completely lost student and the capable student and the excellent student. There's a natural gap, right? Did that come from probability distribution? Did I go to Wikipedia page to choose the distribution? No. I just plot the histogram and it's obvious. There's like a little hole here and there's a little hole there, right? Now, in one dimension, it's easy to spot. Okay? Now, what if I do this? What if I do this? I take the height and I take the weight. And let's say I find the same thing. Instead of having a continuous, I have 2 lumps. I have short and skinny and tall and fat. and then tall and skinny. There are actually 3 clusters. Okay. Now I can draw a picture here, but you see what I mean, just to save time. You'll see that if I plot the data scatter plot, and we'll go into detail when we see that, go to scatter plot, you see a whole bunch of short and skinny and big and fat, and so tall and fat and tall and skinny. And there's like a space in between. So you see, oh, well, there's actually 3 clusters. So you can see that visually, right? Okay. Now, imagine that I want to do this in 4 dimensions. In 3 dimensions, sorry, 3 dimensions. Can I do that? Yes, you can do scatter plot in Mathematica, scatter plot 3D. Okay, scatter plot 3D, or sorry, not scatter plot, list plot 3D, and that will give you 3-dimensional. So you can do cluster analysis in 3 dimensions. How about 4? How about 5? How about 50? You cannot do it, right? So just as, you can do tabular data in Excel, but when it gets so big, you have to go to Python and Mathematica. Same thing here. You can't use visualization anymore, okay? And this is where you don't get a choice. If your data is multidimensional, you can't just rely on visualization. That's not good enough. Let me give you an example of a multidimensional entities. A country's economic performance, right? So if you rank each country by GDP, maybe you get this kind of clustering, right? Poor country, middle of the road, rich country. Fine. Plot another axis, population size. So GDP population size, maybe there's rich and populous, poor and populous, whatever, okay? And anything in between. So there's a little lump here. You can see that, oh, there's a natural grouping. Well, 3rd dimension. What about age, right? Average age. 4th dimension, right? Landmass. 5th dimension, carbon dioxide emission. 6th dimension, infrastructure investment. 7th dimension, inflation. 8th dimension, okay, number of high-tech industry or whatever, it doesn't matter. Now, can you cluster together? Now, intuitively, for example, you can say that maybe Thailand would be similar to, okay, based on this multi-dimension, Thailand is similar to Chile. Okay, similar kind of population, similar level of education, GDP, inflation, blah, blah, blah. And you can do that if you go one by one and see that it's similar, right? But how can you do this for all the countries, for all the dimensions? This is where cluster analysis comes in. Okay, now you're going to have cluster analysis here. You're going to have cluster. Oh, sorry. So that's one thing. That's cluster analysis. Now, this here, when I branch out, I branch from where? I branch from heuristic. It turns out that when I branch from neural network, we will have that as well. So, but let me go to generic first. Okay. So this is called cluster analysis. Okay. So this is one problem. Okay. In the original dimension, you can't see it, you can't plot it, you can't visualize it. There's no way you can imagine. But you can say that Thailand is close to Chile, and maybe India is close to China or whatever. Okay, even though geographically they're not close. Okay, so you can do that. So this is called cluster analysis. You respect the original dimension, but you try to see who's close to whom and see if they kind of lumps into gangs or into a little cluster. Conversely, how about this? How about if I do dimensionality reduction? Now, dimensionality reduction means the original data has 10 dimensions. GDP, inflation, education, crime rate, land mass, all kind of stuff. Okay. But I want to plot countries on 2 dimensions because I want to make a graph. Okay. I want to make 2 dimensions, but each country has 10 dimensions. Okay. Now, this is where dimensionality reduction comes in. Can I create artificial dimension such that when I plot Thailand and Chile on these 2 axes, Thailand is close to Chile and China is close to India and Denmark is close to Singapore. Okay. In this case, I'm not respecting the dimension. I'm respecting the metric or closeness, the distance. I'm respecting the distance. But that distance has been massaged so that I can draw it in 2 dimensions. Now, that doesn't make too much sense right now, but believe you me, this is one of the most useful data analytics in your life. Okay? It doesn't look obvious now. Why? It doesn't look obvious now because from high school, you have always been able to plot anything you see. So when you do regression analysis, y is a function of x. This one y, this one x. At most, y is a function of 2x. And that's it. That's all you see. If you have y as a function of 5x, you don't plot it. Okay? If you have x dimension of 10, you don't try to look at it. You just put it in a table. Well, here, you try to look at it. It's called dimensionality reduction. Now, this one, it's very hard for me to say. The other thing is called space embedding, but that's, you know what? For the purpose of this class, these 2 will be bunched together. These 2 will be bunched together. When you go to a machine learning class, maybe you learn into the nuance between what's space embedding, what's all kind of stuff. Anyway. So that's that. So let's say in the final exam, I'm not going to ask you what space embedding is. I'll say, you know, what kind of job does unsupervised learning do? Well, 2 things, either cluster analysis, whether or not, you know, there's a natural grouping or cluster, and dimensional reduction. Can you squeeze the original 50 dimension into 5 dimension? To 2 dimension. By the way, dimensional reduction, when I said just now, the motivation is to plot, right? So it's always go down to 2 dimension. But in reality, you can use, you can have problem with, say, 500 variable. So 500 dimension. So sometimes you reduce that to 30. You still cannot plot it, but it's actually more useful. Okay. Now this is where it gets a little bit tricky into, you know, space embedding and all that. So dimensionality reduction, think of your motivation as trying to plot. Okay. But the algorithm doesn't really care. I can specify reduce from 50 to 2, reduce from 50 to 5, reduce from 50 to 49. Okay. As long as it's an artificial dimension that's smaller than the original dimension, it's called dimensionality reduction. Okay, but to make your life easy, just visualize trying to reduce whatever original dimension down to 2 to 3. Okay, does that make sense? Okay, or you know, you can think of okay, I can have student's grade, right? Student grade has 3 lumps, right? What if I have another grade? Has to do with how polite you are or how punctual you are. It has nothing to do with knowledge, let's say, but it has to do with professionalism. Okay, so I have another grade, right? So it's 2 dimension, right? So I can plot that, right? I can do cluster analysis, right? But wait a minute. If I do cluster analysis, I can't assign the final grade because the final grade is just a 1 number. So even though I have just 2 dimension, I may want to reduce that to 1 dimension So that once I get the one dimension, I say there's A student, B student, C, D, E, F, whatever. Okay, so dimensionality reduction is not always from 50 to 2. It can be from 2 to 1. It can be 59 to 40. Okay, that's my point. That's all I'm trying to say. Okay, depending on what you use for. I would say something now. It may not make sense to you, but what happened is sometimes, well, I'll just say it, okay? If it doesn't make sense to you, just ignore it. Sometimes I want to make a prediction model. Y is a function of 50x. Y is a function of 50x. Okay. Now, in regression analysis, let's say you have a friend from statistics department. There's a problem called multicollinearity. It's a very scary problem. It's like a sickness. Okay. What it essentially means is that even though you have 50 variable, the data is not really scattered evenly in 50 dimension. It's actually scattered along lower dimension. Okay. Do you want to see a picture? Okay. Yeah, we can draw that. We have time. Okay. Go to here. Okay. Okay. Now watch this. This is your regression equation, regression problem, right? You have data. Right? That's regression analysis, correct? Now, let's say you have a regression analysis in 2 dimensions. Okay? What it means is that I'm just going to say this is all the x's, right? And so the y is like a surface. Can you guys imagine? You see that, right? So y is equal to alpha 0 plus alpha 1 x1 plus alpha 2 x2, or x and y. Okay? Right? Can you guys see that? So that's x1 and it's x2 and that's y. Okay? Right? So this is a regression of y on 2 dimensions, x1 and x2. Okay? This is what multicollinearity means. It turns out that if you look at the x are not spread out in both x plane. It sort of like gathers around here. So when you try to fit a plane on top of it, it wobbles. Okay? Can you imagine that? Well, let's put it this way. You have a chair. You're sitting on a chair, right? Why is it stable? Because it distributes in this plane and that plane. So it's one leg here, one leg here, one leg here, one leg here, right? Right? And you're sitting comfortably, stably. Now, if I design a chair so that one leg is here, another leg is here, one more leg is here, one more leg is here, and I put a seat on it, would you sit on that chair? No, it would wobble, right? Right? It's not stable, right? Well, think of the chair as the regression surface. If the x are evenly spread out, then you have stable platform to make surface. But if in 2 dimensions, it's actually in a line. Actually, it's in 1 dimension. So inherently, even though you have 2x, you only have 1 dimension, except that dimension is along the diagonal. That is a deadly problem called multicollinearity. It means x's themselves are not independent. Okay? They kind of form a line. So you can't fit things on top of that. Well, in machine learning, sometimes I want to do supervised learning, which is y is a function of x. But I have too many x. So instead of doing supervised learning on original 2x, I use unsupervised learning to reduce dimension to 1. Then perform supervised learning on that. Now, this is a very advanced concept. I'm telling you now so that you start to have this picture in your mind, because that is the biggest hack in my professional career. Well, most people's professional career. Sometimes, yes, you don't do just supervised learning or unsupervised learning. You do unsupervised learning as a pre-processing for supervised learning, and you get better result. Okay? Now, so the whole thing, if it didn't make sense, ignore it. Okay? But I'll come back to it. Okay? I'll come back to it.เดี๋ยวพ่อโทรไปลูกอีก10 นาที Yeah. Okay. Right. So, can we switch back to the screen? I do this. No. Okay. I'll be smarter next time. So I do this. I stop share. Switch this. Okay, good. So supervised learning, in this case, again, whoops. Okay, in supervised learning, remember I told you that this is going to be similar to regression. Again, this is sort of like y is a function of x. There are 3 families. One is called tree base, and this is, we'll get into this in detail, by the way. Okay, so don't worry about it. I'm just giving you the lay of the land, as it were. Okay, so how do I do this? It's sort of like okay. I see somebody walking by from a distance, right? From a distance. And I don't know if it's a boy or a girl. Okay? Okay. Now, for some reason, let's say boys are taller than girls. Boys are taller than girls. Okay? So, based on that alone, I have this choice, boy or girl, given height. So, I see somebody very tall, I'm likely to say it's a boy. Okay? This person walks closer. Hey, it's got long hair. So right away, there's a probability that given it's tall and long hair, it's a girl. So maybe it's higher probability to be a girl. Okay? Or maybe short hair, it's probably a girl. This person walks a bit closer and holding a purse. Now, boys can wear purse. I think I have a purse. It's a man purse. Okay? But probability of boys hanging a purse is a lot less than girls, right? So these are all conditional probability. So based on this factor, height, what's here? Hair length, purse or no purse, I end up with the final probability that this person is a boy or a girl. Based on that, I make a prediction. It's a boy. Based on that, it's a girl. Now, obviously, this thing is going to fork, right? So fork by height, fork by hair length, and you can fork as many times as you want, right? So how many branching can you get? As many branching as there are variables, right? So this would be kind of like a decision tree. Okay. Now, Up here, there's something that I haven't told you. It's called down here, up here, down here. It's called ensemble learning. Well, actually, this is a little bit like this. It's saying instead of having just one tree, you have a whole bunch of trees. We'll learn on this. Don't worry. Okay. But the idea of this kind of, before I predict boy or girl, cat or dog, sell or not sell, client or not client, good credit or bad credit, I go through a whole bunch of variables. And each time I get additional variable, I get update probability. This is actually very basic in construction, but I'm not going to cover that here. So that's one way. That's one way of making sort of like supervised learning. Why is it called supervised learning? Because the probability here is adjusted based on your 5,000 samples, right? And basically, based on this probability, sometimes I'm going to make the right call. Sometimes I'm going to make the wrong call. That's accuracy, right? Now, if it overfits, it's going to be not generalized well. But if it does generalize, the next person comes in short, long hair, with a purse. Maybe you have probabilities. Oh, this looks like a girl. So sometimes, it's obvious, right? Short, long hair with a purse, tall, short hair, no purse. Okay, maybe that's extreme end. This definitely look like a boy. This look like a girl. But anything else in between, the probability has to be adjusted. The algorithm, the decision tree algorithm has to adjust. Okay, so whereas with probability distribution, you pick an F, you adjust the A or B or alpha 1, alpha 2, alpha 3. Here, you adjust the probability of going here or here. Okay, right? So you have all the three of probabilities based on certain information. You adjust that to fit the data. Okay. Random forest and gradient boosted tree just means that you have more than one tree. Okay. You learn that in details. So that makes sense, right? You have data based on the past classification. You can get cat versus dog, boy versus girl. Okay. Now, the other family is called nearest neighbor. This nearest neighbor is a little bit easy. It's a little bit like this. You have history of people who are boys and girls with hair, short hair, long hair, with purse, no purse, tall or short, right? This person comes in, has certain length of hair, certain length, certain height, and with or without purse. You try to look at who is the closest in the sample in the past. It turns out there's this person who is almost the same height, just different by an inch. Similar hair length, just separated by 1 centimeter, and both wear purse. What did that person turn out to be? Girl. The new one is a girl. Okay, that's called nearest neighbor. So basically making prediction based on what you saw. Now, obviously, that's one neighbor. Sometimes you have more than one neighbor. So it's similar to 3 people in the past. Well, if it's similar to 3 people and 2 of them are boys, 1 of them is a girl, maybe you say it's a boy. Okay, that sort of thing. So this is kind of like nearest neighbor. Again, we'll be using this in a real, case. Okay. So that's supervised learning. Bayesian is wrong screen. There is naive Bayes and Bayesian belief. I'm not going to go into it. Oops. Right, I'm not going to save this. Now, next week, because we're kind of running out of time, we'll also have supervised and unsupervised. Again, there's reinforcement learning I'm going to throw out. Okay, just so you know, if you like reinforcement learning or robotics, they go hand in hand, but not in data analytics, not so much. Okay, so in data analytics, I'm going to teach you supervised learning and unsupervised learning mainly. Sometimes I make a little more details than you need to know, you know. So this is kind of like meant to be a general map. For this class, for the purpose of this class, sometime I'll skip over some of the details because you don't need to. Okay? Just trust me, it's Michael. So just as right now, when I say decision tree, that has no reference on this kind of artificial brain model. Okay, they're similar to that, but based on brains. So next week we'll do two things. Okay, next week we'll do two things. Okay, we will go into some of this thing, this kind of like decision tree. Okay, but we will also go to similar thing with a neural network. But the neural network takes some building up to. Okay, so let me decide which one I'll bring up in the first part. I'm not sure. Okay, now I kind of shot myself in the foot, ran out of time. I really wanted you to. I wanted to start kick off the term project discussion this week, but for some reason I forgot. so we went over time. So that's okay. Let's just do this. Let's just do this, okay? All of you must raise your hand once. Okay. A, interactive visualization is my cup of tea. B, probabilistic models, statistical method is my cup of tea. C, machine learning is my cup of tea. Okay. A, raise your hand. High. Okay. B, raise your hand. Okay. C, raise your hand. Okay. Okay, fine. I know what to do. Okay, so we can do that. We can do that. It's a little bit lopsided, by the way. Okay, which is fine because to be honest, machine learning is where we're heading. What I can do is this. Okay, let me tell you the game plan. It turns out that from this alone and from my guesstimation, we are going to be this much machine learning, this much interactive visualization, and this much statistical model. Okay, that's sort of like the breakdown. Okay, that's fine. That's no problem. No. Don't feel bad because you know statistical method has been around for 300 years. So you run out of you have so much material to learn from. Okay, and as a project you can do that. I use both, by the way, just because I like AI, I like machine learning, I like advanced technology, doesn't mean I don't use statistics. I use, okay, final word, I guess, maybe as I remember. Remember I told you about this, who's more powerful? Machine learning is more powerful because it applies to more cases. Statistical method is more powerful because if it does apply, it gives you more detail. So here's my philosophy. And this is not just philosophy, it's a best practice. If you can use statistical method, use statistical method. Because it's going to give you a lot more conclusion, a lot more insight, a lot more details. Use machine learning when you cannot. Okay, so don't be one of those data scientists where you say, you know, see distribution and completely normal and say, I'm not going to fit distribution, I'm going to use neural network. That's a stupid thing to do. Okay, if you can fit probabilistic model accurately, robustly, don't use machine learning because it's going to give you a lot more approximate solution. Okay. So, but when you say that most of you are more like into machine learning, chances are it means because the data that you want to work with are more generalized. Picture, image, color, text. These are things that you cannot use probability easily. Okay, there's some linguistic model of probability, but not many. Okay, so now I know what your desire is. I can sort of like plan the rest of the term. Okay, but next week when we come, sorry, have you picked your groups? Raise your hand if you haven't got a group. Okay, so everybody's got a team, right? Okay, so maybe next time you can sit together. Okay. Okay, so I'll see you next week. Okay, I know what you want now. I will plan according. Okay ครับ สวัสดีครับ